Let's look at some molecules in 3 dimensions. The first kind of molecule we're going to look at is a nonpolar molecule. Now, this example should be fairly simple because we've got only 2 hydrogen atoms. These little 2's on here are just the way that the program is differentiating between this hydrogen atom and this hydrogen atom. It doesn't mean anything about electrons or anything like that. They're both identical. The program just wants you to know that there are 2 different hydrogen atoms here. Down here are the atom electronegativities. And so we can see that if we have 2 hydrogen atoms, our electronegativity difference, or our delta En, is going to equal 2.1 minus 2.1, which is equal to 0. And anything below 0.4 is nonpolar. So let's just do a quick chart here. An ionic bond is going to have an electronegativity difference of greater than or equal to 1.67. A polar covalent bond will have an electronegativity difference of between 0.4 and 1.67. That's what this means right here. And a nonpolar covalent bond will have an electronegativity difference of less than or equal to 0.40. So here, in this case, we are definitely have a nonpolar covalent bond. And so we can say that this molecule is nonpolar because there are no polar bonds, right? There are no polar bonds here. And so we can say that the entire molecule is nonpolar. Let's do another example. Let's look at nitrogen gas, which is formed from 2 nitrogen atoms. Now, in this case, we have 2 atoms with an electronegativity of 3. So if I was going to find out my electronegativity difference, well, I hope you can see that it's going to be 0, right? Because I'm going to take 3.0 minus 3.0. That's going to be 0. So we have another nonpolar bond. Hopefully you're seeing a pattern here that when you have the same elements bonded to just itself, then we're going to have a nonpolar molecule because there are no polar bonds in this molecule, so the entire molecule is nonpolar. Let's just, for the sake of making sure we're clear, here's a 3D example of oxygen, and because oxygen has only nonpolar bonds, because it has an electronegativity of 3.5, then the entire molecule is considered nonpolar. Now, I do want to point out that this is a 3D model, and so it's not showing us right now that each of these oxygen atoms is also going to have a lone pair, 2 lone pairs, right? I just want you to kind of keep that in mind, that we still do have our lone pairs here. They're just not being shown in this particular model. Let's look at another example. Let's look at one where there is a difference in electronegativity. So here is hydrogen bonded to fluorine. Now our electronegativity difference is definitely not going to be 0 this time. In fact, we're taking the most electronegative element, fluorine, 4.0, and taking a pretty, fairly low electronegativity atom, hydrogen. So we end up with a really big electronegativity difference of 1.9, right? And so this is definitely, this would actually seem to be an ionic bond. Now in this case, because hydrogen is considered a nonmetal, we're going to say that it's just a very, very, very polar bond, right? It's a very, very, very polar bond because it's between a nonmetal and another nonmetal. That said, there are times when we can see hydrogen act in as though it's forming ionic bonds. But in this case, let's just know that these are going to be very polar molecules here. And let me show you something really cool. We can actually look at the electrostatic potential. So we can see that this molecule is actually far more negative on this side than it is on this side. And if you're wondering why, let's look at the electron density. We can see that the electrons spend way more time around the fluorine, which is the more electronegative atom, than they do around the hydrogen. Way more time. The electrons want to be around fluorine way more than they want to be around hydrogen. And so the impact of that, since electrons are negatively charged, right? If I drew a bunch of, let me just draw some electrons in here. Now, keep in mind that there aren't a whole lot of electrons in here, right? But if I just drew some electrons, we would see that most of them want to be around the fluorine, right? I'm not actually counting these, just pretend that this is sort of a cloud of electrons. We use electron cloud models. And even though there certainly aren't this many electrons in this small molecule, I'm trying to demonstrate that you're most likely going to find the electrons spending a lot more time around the fluorine than you are around the hydrogen. The impact of that is that even though the molecule doesn't have a charge, right? There are the same number of protons as there are electrons. We're still going to have what is called a partial charge, or like a separation of charge in the actual molecule. Because they're spending way more time over here, the protons that are inside our hydrogen atom, right, that are here in the center, or the one proton that's in our hydrogen atom, isn't as balanced out by its electrons. Remember that we've talked about sort of balancing out our protons and electrons, and that when you have a proton matched up with an electron, then you can sort of imagine that the charges are canceled, right? Or that there's no overall charge. Well, in this case, the hydrogen's sort of missing its electron, right? Because the electron is going to spend way more time around the fluorine than it will around the hydrogen. The impact of this is that even though there's no charge on this molecule, we do see that this side of the molecule has more of a negative charge. I didn't say a full negative charge, but it has a partially negative charge. And this side of the molecule has a partially positive charge because it's sort of separating out those electrons. Let me erase some of my little electron dots in here and show you how we show that. So to show that we have a partial charge, there are two things that we do. One, we can draw an arrow to say, hey, this is the positive end of the molecule. You draw a plus sign and then extend that out and draw an arrow toward where the electrons like to hang out. The plus sign goes to the positive end of the molecule and points toward the direction that the electrons want to hang out. The other thing we can do is draw this symbol and say that there's a partial negative charge on this side of the molecule and a partial positive charge on this side. These symbols just mean that it's a partial charge, not a full charge. It's not like we have one whole extra electron over here. It's just saying that the electrons are generally hanging out more on this side than on this side. But let me erase my drawing and show you that this program has a really nice depiction of that. So let's take this away. And so if we were going to show the bond dipole, that's the arrow that I drew is a dipole arrow, right? So the bond dipole can be drawn like that. And let's see how close my representation is to what this great program shows us. So look, it's an arrow with the plus sign over at the positive end, or the partially positive end, and the arrow pointing toward the partially negative end. Now, if I show the molecular dipole, in this case, it's the same direction, right? It's just showing that this little plus side is on one side and it's pointing in the direction of the more electronegative side. Now, in this case, it's being drawn like this, just showing that the electronegativity is more on this side than on this side. But really, it's kind of a simple thing because it looks a lot like our bond dipole arrow. Let's look at a little bit more complex example. Let's do water this time. Now, but actually, before I switch over to water, let's draw a Lewis structure of water. So if we looked at our periodic table, we know that oxygen has 6 valence electrons. So I'm going to draw them like this, 1, 2. I'm not going to double up any electrons on my invisible box until I draw 1 on each side. Well, there's 1 on each side, so now I need to double up because I still have 2 more electrons. So now I see that I have 2 lone pairs and oxygen wants to form 2 bonds. Well, water is H2O, so now I need to draw 2 hydrogens. And each hydrogen has 1 valence electron. I can bond these individual electrons, these lonely little electrons for each atom. And now all three of these atoms are very, very happy. We need to be able to know what the molecular geometry is, though. And you might be thinking, well, it's easy. Look, it's bent. And you're right, it is bent. But what if I had drawn it like this? What if I had drawn my oxygen atom like this? It still shows the two lone pairs, and it still shows the individual electrons on each side of my individual box, on each side of my invisible box. If I draw my hydrogen atoms in here, I can draw them like this. And I could bond these lonely electrons like that. Well, this is also a correct Lewis structure. But in this case, we would see that it has a linear geometry, right? So how do we know that water has a bent geometry and not a linear geometry? To answer that question, we have to remember that each of the lone pairs is also an electron domain or an area of electron concentration. And they do not form 90-degree angles with the other electron domains. That's because we are in three-dimensional space. And so what actually happens is, and I'm going to do my best to draw this, what actually happens is if we drew this in three-dimensional space, we would try to draw something like this. We would draw an oxygen atom bonded to a hydrogen atom, bonded to another hydrogen atom at an angle here. And this is actually going to be a 109.5 degree angle. And then we have to draw in our lone pairs, right? So we'd have one lone pair here and another lone pair sort of extending to the back like that. So there's no way, it doesn't matter if we switch the lone pair with this hydrogen, whatever, these hydrogen atoms are always going to be at an angle of 109.5 degrees with the oxygen at the vertex of the angle. And so we know that it cannot be linear. So even though this is a correct Lewis structure, it does not show the correct molecular geometry. So now that we've got that straight, let me erase my drawings and bring up a 3D model of a water molecule. So here is water, and just as we said, we have this bent shape. Now in this model, it's not showing us the lone pairs, but I'm going to add them in, not in a beautiful three-dimensional way, but I just want to remind us that we have some lone pairs right on this side of the atom. Now our electronegativity difference does exist here. Let's decide whether these bonds are polar or nonpolar. So we're going to take 3.5 for oxygen and subtract 2.1. And so our electronegativity difference is going to be 1.4, and that falls within this range of a polar bond. So we definitely do have a polar bonding molecule here. Now, what about the molecule's polarity? Well, to figure out if the molecule itself is polar, which you might think like, well, of course it is. Not so fast. There are definitely times when we have polar bonds, but a nonpolar molecule. But in this case, let's see if we can draw our dipole arrows showing the polarity of these individual bonds. So I'm going to draw a dipole arrow on this side, which is the plus side, and pointing toward the more electronegative side, right? So this is going to be the more positive end of the atom. It's going to be the more negative end of the atom because the electrons are going to spend way more time around here than they're spending around the hydrogen. And I'm going to do the same thing over here. Now let's take a look and see if that is accurate. We're going to look at our electron density. And yeah, sure enough, we've got electrons hanging out way more around the oxygen atom than they are around the hydrogen atoms. And if we look at our electrostatic potential, we can see that there is a partial negative charge toward the oxygen because it's hogging those electrons, right? It's not sharing them equally. And we have partial positive charges by each of the hydrogen atoms. So if I was going to draw that in, I could say that this hydrogen atom has a partial positive charge, this hydrogen atom has a partial positive charge, and this oxygen atom has a partial negative charge, right? Now, the question I want to ask you is, what about my molecular dipole? So let's say I wanted to show if this molecule was polar or not. I want you to kind of imagine that I'm going to erase these arrows. I want you to kind of imagine that we're putting these arrows together at the top of the oxygen here. So this arrow that was pointing this way, I'm going to sort of draw it right here. And this arrow, I'm going to draw it right here, and it's looking a little messy. What I want you to imagine is that there are some people here maybe pulling on the arrows or pulling on this oxygen atom or pulling on the electrons, right? Here's my person playing tug with these electrons. So they're pulling and pulling and pulling. What's going to happen to those electrons? Are they going to go in this direction? Are they going to go in that direction? Hopefully you can really picture it, like really imagine what if both of these tiny people pulled on the electrons? Since they're kind of pointing in opposite directions, what would happen is the electrons would actually be pulled straight up because they're fighting against each other going to the left and right, but they're both also pulling the electrons straight up. And so if I was going to draw the dipole for the entire molecule, the molecular dipole, I could draw one like this, and we would see that absolutely, yes, this molecule is polar. So let me show that. There it is. Right? There's our molecular dipole arrow showing that our molecule, the entire molecule, is polar in this direction. Right? It has a slightly negative end and a slightly positive end like that. Let me erase my fun people. And let's see if we can do one more example here. Remove this. I want to show you now that we can have a situation where we do have polar bonds, but a non-polar molecule. So let's analyze this molecule right here. First, we know that we have bonds between carbon and oxygen. So if we want to find our electronegativity difference, whoops, let me do that in black. If we want to find our difference in electronegativity, we would say take the oxygen, 3.5, and subtract the carbon, 2.5, and that gives us an electronegativity of 1.0. Well, that falls between this range. And so these are polar bonds. Now, I wonder if you could draw the dipole arrows here. Which one is the less electronegative atom? That's carbon. And so the plus sides of the arrows are going to be at the carbon, and they're going to point toward the more electronegative atom. So we can imagine then that the electrons are spending way more time around the oxygen atoms than they are around the carbon. So let's look here at our electrostatic potential to see if that's true, or electron density first. So yeah, look, we've got a darker color indicating that electrons are spending more time around the oxygen atoms. And if we look at our electrostatic potential, we do see that there's a slightly negative charge on the oxygen atom sides and a slightly positive charge around the carbon. You might be really tempted to say, oh, well, then this is a polar molecule. But it turns out that if we try to draw a molecular dipole, a dipole arrow for the entire molecule, these individual bond dipoles would completely cancel out. They are exactly opposite. Again, imagine if we had our little people here tugging on the electrons using this as a rope. I hope you all like my pictures. Here's my person tugging. These are the legs. Well, they wouldn't get anywhere if they're equally matched, which they are because they're representing both oxygen atoms. They're not going to go anywhere. They're not going to pull the electrons anywhere, right? So even though I know that you're probably thinking like, wait, you just told me there's more electron density here. You're right. But what I'm trying to show you is that they actually end up canceling each other out. So when we talk about the molecule as a whole, we say that the molecule as a whole is nonpolar, even though it has polar bonds. So let me click on this to see if there's a molecular dipole. And there's not. There is no molecular dipole arrow. See, if I show the bond dipoles, there are arrows showing the dipoles of each bond. But if I click the molecular dipole, nothing pops up. We just see that there's like a little yellow dot as though it's trying to. And if you're like, wait, turn it around, I'll turn it. Look, there's no molecular dipole because the bond dipoles of each oxygen atom are completely canceling each other out.